Welcome back. We're in circular motion. Worksheet number 2, problem number 2 here. Let's get into it. Car drives quickly over the top of a semicircular hill, and it's got this radius of 40 meters there. We should go ahead and let's draw that out there. So this radius of curvature is 40 meters. Boom. Draw a free body diagram, force diagram for the passenger here. So let's think about this passenger here. We go and draw a free body diagram, so we'll go ahead and do that off to the side here. And clearly, they're going to have gravity pulling them straight down. Great. Force of gravity, or we can just simply make that m times g. Easy. And then you say, oh, well, maybe he's got a normal force, pushing him up. Maybe he's pressed into the seat there. That would make most sense. And so, yeah, I'm kind of assuming that something is pushing him upwards there. Are these values equal to each other? Well, normally I might say yes, but I think about this and I go, well, let's think about what he's doing here. And I go, okay, at this point right there, he's moving to the right-hand side, and he's moving quickly, it says. Okay, great. Well, he's going over this hump here, and I look at this hump, and it's a semicircular hump, which I already know, and I go and I draw the path that he's taking. He's going from here up there and then back down here in his nice little soapbox car that it looks like we've drawn there. And I go, hey, wait, that looks like he's going in a circle, right? At this point right here, he's going in part of a circle anyways. At this point here, his velocity was pointing that direction. At some point later, his velocity is going to be still tangent to the path there, but it's going to be pointing in a different direction there. And so his velocity is changing even if he's at a constant speed there because it's changing direction. So now I'm loading all this new information into my head and going, wait, this means that at this point right here, he must be accelerating towards the center of the circle or perpendicular to my velocity there if the speed of this car isn't changing, but the direction is. Now, even if the speed was changing, the direction is still changing, and so you must have some acceleration that is pointed centripetally there towards the center. So I'm thinking about that. No matter what's happening in the situation, he must be accelerating towards the center there. And so now I'm thinking about that and going, wait, that means that when I add up these forces here, I'm going to get unbalanced forces because I need to have it accelerating because it is accelerating because it is changing its direction there. And so what speed would be necessary for the car to lose contact with the ground? Interesting. Okay, so now we're doing the free body diagram for the person, but we're asking about the car here, and then we're going to relate the car back to the person here. So let's think about the car for a second. If the car was going to lose contact with the ground, well, the car is in contact with the ground because gravity is pulling it down, right? Oh, right, gravity is pulling it down, and it pulls it down, and the tires and everything into the ground there, and then we got two surfaces pressed into one another, so that sounds like a normal force, and then the ground pushes back up on those wheels there. Now, if the ground wasn't there getting in the way, then they wouldn't be pressed into one another. Or another way to say that is, hey, if the force of gravity is pulling this thing down, and if the ground wasn't there, you know that the acceleration due to just gravity, or you might say g, would be 9.8 meters per second squared, right? If the ground wasn't there, their change in speed would be 9.8 meters per second every second there, if the ground wasn't there. Well, the ground is there, clearly. We're not erasing the hill here, but I'm thinking about this and go, the person is accelerating towards the center, and at this point right here, the car is accelerating towards the center for the exact same reasons of the velocity is changing here. And so now the car is accelerating downwards. Now I think about this and I go, wait, hold on. If the car is accelerating downwards, what's causing that acceleration? Well, forces, clearly. What forces do I have acting on the car or the person? Because it's basically the same thing. I have the force of gravity pulling these things down. And then if these things are pressed in something else, I got the normal force pushing them back up there. Well, thinking about the car here for a second, if it's accelerating down and I'm trying to figure out when it loses contact with the ground, that means that the ground's not getting in the way. And if the ground wasn't there, then the car would be accelerating like this here. And I know that even if the car is in contact with the ground, that it is accelerating, and the only force that's going in that direction to cause that acceleration is the force of gravity. So I think about this for a second and go, wait, hold on. That means that for the car here, this is my car now, for the car here, the car to lose contact with the ground, you'd have the force of gravity on the car, and that's it. Well, the only way that's true is if the ground isn't getting in the way, or maybe another way to say that is, we know that the car must be accelerating. What if the force of gravity, if the ground wasn't there, the force of gravity would cause this acceleration? What if that acceleration was this value? If that was the acceleration needed to go around this corner here, well, then there wouldn't be anything pushing it back up, because all of that force would be put into changing the motion of this vehicle, changing the direction that this velocity is going, that the car is going. Okay, so wait, hold on. That means that this acceleration here, for the cars to lose contact with the ground, the acceleration, and maybe we add in the centripetal acceleration to make this car go around there in the first place, if that was equal to what gravity naturally produces, you might say, gravity naturally causes there, if those were equal to one another, then yeah, I would have the full force of gravity is causing this thing to change its direction there, and now it actually wouldn't be pressed into the ground anymore. Okay, so that means that we're solving for when the acceleration, the centripetal acceleration needed to go around this corner here, this curve, this semicircle, would be this value, or at least at that point right there. So now let's go back, and we're going to continue on with the person there and not do that in green because that would be confusing here. The person here is our system. And so now we're going, okay, great. Well, now if the centripetal acceleration is equal to 9.8 meters per second squared, well, then that means that I need to augment my free body diagram. I'm going to do that free body diagram. That means I have the force of gravity going down, and then nothing is going to be pushing this person back up, because this car beneath them is going to be accelerating down at this rate. And then as that car moves away from them, well, the floor, literally the floor and the seat is moving away from the person as the person is moving into the car and the seat there, the seat and the floor there. So it's like the same idea as the elevator problem, where we cut that elevator cable and now the elevator is in free fall. Is the guy going to be pressed into the bottom of the floor? No, because as the guy falls towards the floor is falling away from him the exact same rate. Well, the car is falling away from him at the same rate that he's pulled downwards as well, or he's accelerated downwards. And so, then he won't actually have a normal force going up. What would that feel like for him? No normal force on him? It would feel weightless. But that's why when you go over big humps like this and you're going fast here, it feels weird in your internal organs there, because they get different normal forces on the internal organs. Think about that for a minute. Okay, let's get back to the problem here. What speed would be necessary here? Okay, so that's our setup there. We're going to this is going in circular motion here, so let me go ahead and define our coordinate plane. Our coordinate plane is as you'd expect. I have something that goes in the tangential dimension, and I have something else that goes in the radial dimension. Going towards the center is the positive radial dimension, away from the center is the negative radial dimension, and the tangential dimension will say the positive version. The positive side of that is whichever way you're currently going there. Make that easy. And so now let's go ahead and let's sum these forces up in the radial dimension there. And that's equal to mass times acceleration. We've done this a ton of times here. We got mg. It's pointed towards the center there, and towards the center is positive direction there. So careful. It is pointed down, but down is, well, at this point right here, anyways, that is positive direction there. And so it's equal to m times a. Whoa, check that out. Hey, the mass cancels out here. That's good, because I didn't know the mass of this person nor the car there. So that's good. And then I go, hey, the acceleration here, well, I know something about that acceleration. I know that the centripetal acceleration is the tangential velocity squared divided by that radius there. Now, you can put a sub c, and I did kind of put that over there, so I'm going to go ahead and keep going on with that. Again, the a sub c stands for centripetal, and I usually don't use that, though, because it could stand for centrifugal, too, because that starts with a C as well, but I did write it out there, so I guess I'll keep going for this. So I'm going to go ahead and substitute those things in there. And so I know that the tangential velocity squared divided by the radius is the acceleration there. Now we're trying to figure out how fast it's going to be going. So we're trying to figure out the tangential velocity there. So g times r, move the r to the other side and take the square root of that. And now that's the tangential velocity there. We know that anytime you take the square root of something, it's really positive or negative. In this case, we know that it's actually the positive value because we defined that it's moving in the positive tangential dimension, so it's really just a positive value. But I'm always thinking about that every time. I go and I put in the values I know. I know that's 9.8, and I know the radius was 40 meters, I believe. Yes, it is. And then I grab my handy dandy calculator and go put that stuff in. I have one on the screen here for you. So I put it all in one go here in one line here, make it nice and succinct, and I can catch my errors and such. 19.79, that rounds to 19.80. 19.80 meters per second is the speed that it would go when it loses contact with the ground. Notice that we solved it for, this is a boundary condition problem here, we solved it for when it has lost contact with the ground. Well, anything just less than this, it's going to have some normal force. Anything greater than this, well, now it's not even staying on the road and it's like floating off the road. It's like, being launched off of the ground there and it's flying through the air. Oh, is that how ramps work? And, you launching off something and then actually making a jump there? Yeah, it's the same idea here. Okay, cool. That's it. Have a beautiful day. I'll see you later. Bye.